Oh, here today. A few examples. Don't know if you want to pass them around, have a look. It's a bit big, that one.
That is fiberglass. GRE, glass fiberglass epoxy. I may get round to this time. If not, it'll be next week. So the yellow one we spoke about, that is an electrofusion one. Oh yeah. That is how it's big. Okay, I was talking last time about halfway through the second lecture. Hopefully I should finish off today on polyethylene, and then next week I can start with composite pipes. I might get some composite pipes done today, but it depends how much I digress. Right, we talked about qualification testing of thermoplastic pipes. Actually, all qualification testing of non-metallic pipes involves similar procedures, because these pipes all fail by the process that we call stress rupture or static fatigue. So you apply a load, and sometime later the sample fails. So it's a time-dependent yield, or if you're unlucky, it's a time-dependent growth. So you have a whole bunch of samples in a water bath at constant temperature, and you wait for them to fail. And when they've failed, you plot this graph. So this is a graph. The vertical axis is hoop stress, PD over 2T. Actually, it's a log-log graph, so it's log of hoop stress versus log of time to failure. Now, this type of procedure, again, is used for all non-metallic piping. We're talking about polythene today, but next week I'll be talking about the same graph in relation to fiberglass pipes, except the failure mechanism is different. But that doesn't matter, you can still use the same graph. So what do we do here? Well, if you have a company and you're developing a plastic pipe product, you have to show that you know this relationship between time to failure. Remember, the dependent variable is on the horizontal axis this time, just to make it confusing. So it's like a fatigue curve. So the time to failure and how it is related to the hoop stress which is applied to the material. Now, design life, if you're working for the oil and gas industry, is 20 years. The design life, if you're working for gas or water distribution, is 50 years. In fact, in some cases, it may even be 100 years. You'll be long gone by the time your product reaches the end of its design life. Well, I'll certainly be long gone anyway. You can't be expected to test the product for that period of time. But what do you think? What is a reasonable length of time you might be expected to test products for before you can put them on the market? Give me a guess. How long would you test for? A week? 2 weeks? 10 years? What's a reasonable time?
Can you repeat the question?
You're doing tests over a period of time. You have to do those tests before you can sell your product. What's a reasonable time that a company could be expected to do the testing for? 1 day. Not how many pipes up here. Or you?
No, it's
I would sit on the graph. Don't read the scale on the graph. Come on, you've got a plastic pipe company. Whenever you visit a plastic pipe company, you see all the extrusion lines, just like I showed you in the first lecture. There'll be about 10 or 20 of those. They'll all be running, and you won't see many people around. But the other thing that you'll see is in the lab, there will be these big vats of water with pipes being tested at constant pressure. You tell me suggest to me what is a reasonable length of time. You have to be able to extrapolate into the future, up to 20 years or 50 years on a log scale. So what's a reasonable time that you might be expected to carry out these tests for? It's not an hour, it's not a day, it's not a week. A month. Well, you're getting better. But I still wouldn't buy any pipes from your company. You have to let me have a note of your name, just in case you try to sell me better.
6 months. 6 months.
Oh, well, we're getting better.
1 year.
Actually, it's been agreed by most people that a reasonable period of time is 10,000 hours. And if you calculate 10,000 hours, it's a bit over a year. It's about a year and 2 months. Something like that. So that means you have to do this relationship. Before you can even start selling product, you have to get this relationship. And there are a number of standards that refer to this. So and the standards will tell you how many points you need to have. So what do? You put a pipe under constant pressure, you wait for it to fail, and you measure the time to failure. And you do that for several different pressures, so you get many different times to failure. And it's very difficult to get these long time points, because it's like trying to hit something with a gun when it's far away. It's trying to hit a far away target. You don't know what it's going to be when you're doing the original testing. You know, you imagine you apply, supposing you apply this pressure, hoping to get 10,000 hours. Well, the thing might just fail at 9,000 hours, in which case you're stuck. You've got to do it again. Or it may still be unfailed at 10,000 hours. Now, actually, the standards tell you, one of the standards says that you're allowed, if you have a pipe which is unfailed after pressure testing at 10,000 hours, it's like a fatigue test. You can just call it a run out point. You can put that point on the curve if it hasn't failed. know it's an underestimate, not an overestimate. So, the next thing you do, you have your relationship here with all these different points. You fit the best fit line, so you fit the best fit relationship between log of hoop stress and log of time to failure. And all of the materials that we deal with, empirically, there's no law which says that this should be so, but empirically, they all usually show a fairly good linear relationship between log of hoop stress and log of time to failure. So you plot the best fit straight line. You all know how to plot a best fit straight line, I'm assuming. I'm not going to make you do it, it's all right. But you know the statistical procedure, least mean squares, best fit, straight line. One person that you know. Least mean squares, best fit, straight line. And that's this line here. And there's your 10,000 hours. And there's the design life. It looks like just a very short time between the 10,000 hours and the design life, but that's 20 years or 50 years. It's accepted that it's reasonable to extrapolate a line such as this by about 1.5 to 2 decades in time. In other words, if you do tests for 1 year, then you can extrapolate that to 20 or 30 years. Okay, so there's your relationship. It all looks simple, but there's a little bit more to it than that. So you understand this idea of the, and I often ask this question in exams. You understand this idea of the best fit straight line. However, the best fit straight line isn't a basis for design, is it? Because you can see that not all of the points lie. You wouldn't expect them to. Because the product can be variable. In fact, the product variability is one of its properties. So actually, you're measuring 3 things here. You're measuring the slope of the line, you're measuring the intercept of the line, which gives you the equation of the blue line, but you also measure from your statistics. Remember, you get an upper confidence limit and a lower confidence limit. You remember those? And what you must take when you design the pipe, of course, is you must take the lower confidence limit, not the mean line. Because if you take the mean line and use this as the basis of design, then you might get one of these points which lies below the line. So you try to avoid that problem by taking the lower confidence limit. Now, when you read through stuff, you talk about some standards refer to the lower confidence limit, some standards, that's this green line, and some standards refer to the lower prediction limit. And as far as our course is concerned, we needn't trouble ourselves with the difference between these two. It's simply the lower estimate line which enables you to ensure that most of the time your pipes won't fail. And in fact, the lower confidence limit, if you remember, the thing that we usually plot is the 95% confidence limit. Do you remember that? It's 2 standard deviations. Remember, 2 standard deviations from the line gives you 95%. If you haven't done that, or you don't remember it, write it down now. So your lower confidence limit is just the line minus 2 standard deviations. And actually that green line, so there you are, you take a green line and you extrapolate that to the design life. And that is called your hydrostatic design basis. That's the design basis for your pipe. That is the rating for your pipe. That is how you define it. Now, there are other factors applied to that, depending on the fluid which you're dealing with, the country, the rules of the place where you're installing the pipe. So there will be a further safety factor applied to that. But the H2B is the fundamental thing, the hydrostatic design basis, and that's this point here. And there are other various derating factors relating to safety. For instance, if if you transport oil, then you'll have a different safety factor from the one that you have if you transport water. And if you transport gas, you'll have an even larger safety factor. So we don't need to go into that. We just need to talk at the moment about the hydrostatic design basis. The other thing to note is that although this green line, I've drawn it as a straight line, many of the textbooks do that as well. It's not actually a straight line. You have your mean line. Here's your mean line with your experimental points on it. There's your mean line, but your lower confidence limit is actually a curve. It doesn't curve very much, but it's a curve. So it's actually slightly trying to make it curve. So you'll notice that the further you go into the future, the more this goes down. It reflects the uncertainty of the future. And the other thing, the thing that governs the position of this lower confidence limit, the thing that governs its position, of course, is the scatter of the points. So if you're a good company and you make a very, very consistent product, and there's very little scatter or variation in the quality of the product, then your LCL will be near to being a straight line, and it'll be near to best fit straight line. If you had a product which had a lot of scatter on the points like that, then your LCL would be much lower. It would be much more curved. So using the LCL rewards the supplier, rewards the manufacturer for making a good quality product.
Question. Do we have for this product expiry date in this case? Yeah?
We don't have not an expiry date, we have a design life.
Okay.
When you get to the design life, there's a big debate about what you do with it then, if it's still working. We've got stuff in the North Sea that's 20 years past its design life. And you still can't make up your mind what to do. Do reassessments, things like that. In principle, you should take it out of service. Sorry, what, you were going to ask something
No,
else?
just was question. If it's coming down, it means you should have some design. I mean, expiry date.
We don't have expiry date, we have... Don't get this wrong. Think again, the test that we do is this stress rupture test. You apply constant pressure, you wait for the material to creep and form the parrot's beak, wherever it's gone. It doesn't mean that the product gets worse. The fact that this line goes down does not mean that the product deteriorates. It's simply the relationship between the behavior of the material and time. It doesn't mean it's getting worse. You can take a product like that out of service and test it, and it will probably be as good as it was when it was new. So there isn't an expiry date in the sense that you were thinking about. Right, so there we go. And this long-term stress is sometimes quoted as a nominal pressure rating. But the important thing is this HDB. Now, talked about this now in relation to polythene. This is what they did when they installed all the first polythene pipes in the 1950s and 1960s, replacing cast iron pipes in many, many countries. What could go wrong with this procedure? Because something did go wrong, something went seriously wrong with this procedure. The other thing that I mentioned, I think I mentioned it earlier, is this is used for all non-metallic pipe systems, but only one failure mode is acceptable. So that relationship can only apply to one failure mode. If there's more than one type of failure mode, you can't apply that. And it only applies if failure occurs in the pipe body, not in the fitting. Anything fails in the fitting, the whole product group fails the test. So you're relying on the manufacturer to be able to design and manufacture a fitting which is stronger than the rest of the pipe. And as I said, there's only one failure mode. Anybody tell me what can go wrong with that? So you've got 10,000 hours here, just over a year, and you've got your design life, which is here. What can go wrong with that? And you're only allowed one failure mode, and the allowable failure mode is the Paris peak. Well, what they found is that they found a few years into the performance life of these pipes, they started getting failures. And these failures were not predicted, and they were not Paris peak failures. They were slow crack growth failures. Remember, I mentioned this previous time. Remember, we have two failure modes. We have the attractive one, ductile failure, and we have the one which occurs due to slow crack growth in the material. And slow crack growth occurs either from damage, either from a scratch on the bore or on the exterior of the pipe, or I think I mentioned it can also occur in fittings. A poorly designed fitting, or if you have a sharp corner in a fitting, or when you do your weld. I mentioned this, I remember mentioning this. I don't remember much, but I remember mentioning this. When you do your fusion bond, butt fusion, remember you get a small bead here. That's just one wall of the pipe. So you push the two ends of the pipe together, you get a bead, and of course here you have a stress concentration from which a slow crack can grow. So that's what happened. Found this failure mode which nobody thought of, nobody had considered. So it stopped doing this and it started doing this. So the problem with this procedure is that it only works for one failure mode. There is always a potential difficulty if some other failure mode exists which you don't know about, which can come in between the ends of your test period and the end of the design. And that is what happened. All these pipes started falling apart. It was an absolute disaster. The plastics companies were getting really, really worried. The people making the polyethylene for the pipes were getting really, really worried. They had to go right back to the drawing board and start again. That's just listed all the standards. Ignore that. Right, let's just look at before I go on and tell you what happened. Oh, I should turn that on. That's a good idea. There you go. Before I go on and talk about what actually happened, let's just look at the failure modes, all the different things that can happen. Fittings, couplers, butt welds. You could have mechanical failure of the coupler body. You could have ejection of the pipe body from the coupler. You could have failure of the weld, or you could have, as I showed there, slow crack growth initiated by part of the weld or fitting. In the pipe body, you can have ductile failure, that's the parrot's beak. You can have slow crack growth. Environmental stress cracking is slow crack growth in the presence of a solvent. There are various environmental components which you can get in pipes which affect and accelerate slow crack growth. In fact, with most thermoplastics, you will find that there are certain classes of fluids which affect their behavior. It turned out with polythene, the worst material for producing slow crack growth is actually detergent-like materials, which is a real pity because the other application for plastic pipes in the 1950s and 1960s was washing up bowls. And actually detergent is the worst thing. The main tests for slow crack growth on polyethylene still use detergent as the sensitizing fluid. So, slow crack growth, which is just continuous growth of a crack until it gets to a critical size. Environmental stress cracking, there's the same thing with the solvent present, which makes it happen more quickly. And finally, the other thing you can get is chemical degradation, which I won't talk about too much. If you transport something really nasty in the pipe, which can damage the thermoplastic, you can get actual chemical degradation of the pipe. The most common form of chemical degradation, which you guys, if you live in hot countries, not like this one, where you get a lot of sun, but the worst form of degradation is due to ultraviolet light in the sun. So if you're installing polythene pipes, it's not a good idea to pile them all up by the side of where you're going to install them and leave them out in the open under the sun. It's okay in this country, but it wouldn't be good in Oman or Saudi Arabia or anywhere like that, because the damage caused by the UV would actually severely reduce the molecular weight of the polymer. Anyway, these are the failure modes. How many of those are allowed? None of those. So no failings in fittings, couplers or butt welds. No failures allowed. As I said, the joint must always be stronger than the pipe body. So there you go. I'm going on at this great length. That's the ductile failure. That's slow crack growth. Usually with chemical failure, you see cracks in the material. Actually, if the pipe is under pressure, you will get it turns from a ductile material into a very brittle material, and you get cracks growing perpendicular to each of the two principal stress directions. So you can see, I don't know whether you can see, but I can just about see on here. We have cracks in the axial direction and cracks in the hoop direction when the pipe is under pressure. And that's a pipe that's been subject to UV. That's the sort of behaviour that you get with UV. So if you come across a thermoplastic pipe and it's got this pattern of cracks at right angles to each other on the outside, it's probably UV induced cracking. Right, so that's not allowed, that's not allowed. The only one that's allowed is the parrot speaker type fracture. Right, so this is the problem that we had. This is the same graph as we had before, log of hoop stress versus log of time to failure. There's our fundamental relationship that we use for design. But the thing that we didn't know is that there's another, and remember we call this line a regression line, just because it's we use the procedure called linear regression, the least mean squares method of getting the line. What we didn't realise is that sometime between 10,000 hours and the design life, there's another failure mode. And that's the failure mode which came in and caused all the early thermoplastic pipes to fail. So this change is not seen in a 10,000 hour test, the qualification temperature. How do you think you might... There are two problems really. One problem is doing the qualification test, so you can guess whether that's going to happen or not. And the other problem that you have is getting rid of the problem. Let me ask first of all, what would you're an engineer, you've just been told about this, what would you do to the qualification test to try to avoid this problem? What would you do? Incidentally, all this work was done, all the pioneering work in this area was done by British Gas, as was up in Cramlington. We led the world in design of thermoplastic pipes 30 years ago. Now all they do is supply energy and try to rip you off. Okay, you've got this problem. You're in charge of the test procedures. How would you change the test procedure to try to spot whether this will happen or not? Let me have a suggestion. Pardon? Yeah, that's a bit expensive though, isn't it? It's a bit inconvenient. You've got a guy down the road who's got a failed pipe. You say, oh, can I just do some testing for another 10 years? So what's a better answer than that?
Take samples out of in-service pipelines.
Take samples out of pipes. What do you do with them? Look at them? Well, you're shrugging your shoulders. You take samples, what do you do?
What I mean is you could, if you had a sample for an in-service pipeline, it would have already had an extended period of testing on it.
Yeah, well, I mean, that's how they knew about this. The pipes failed and they took them out of service and they characterised the samples. And they found that they had slow crack growth. But it didn't solve the problem. So you have two problems. What do you do to the... Let me have another suggestion what to do to the qualification procedure. No suggestions, so you're stuck. So you give up, you go back to using cast iron pipes. They didn't go back to using cast iron pipes. What did they do? You what? That's what we just described, testing different pipes. It says test different pipes at different pressure. That's what that curve is. You do, actually, what all plastics people do when they want to accelerate a result, when they want to get a result to happen earlier. And that is, they do tests at higher temperature. So instead of just doing tests, this temperature here is the design temperature, the qualification temperature. So your pipe is qualified to operate at the temperature where you obtain those results. You can't run at a higher temperature. But in the testing procedure, you can run at a higher temperature, and that accelerates everything. So if you do tests at a number of different, the answer is to carry out stress rupture measurements at a range of elevated temperatures. So that's 20 degrees C, 40 degrees C, 60 degrees C, 80 degrees C. And of course, the strength comes down as you increase the temperature. With thermoplastics, the strength comes down substantially as you increase the temperature. But you see, the other thing that happens is the second failure mode, the transition point. You see you have a knee in the curve. The transition point in this curve moves to shorter and shorter times. And eventually, if you test at a sufficiently high temperature, you can get this transition to occur in a lot less than 10,000 hours. So you can tell whether this is going to happen or not. And that's what they did. For thermoplastic pipes, they changed the qualification procedure where you had to do tests at least 4 different temperatures and actually get four regression curves. So due to the temperature dependence of the two processes, the transition moves to shorter times at higher temperatures, so it can be observed at times less than 10,000 hours. And there's a standard, if you want to have a look at it. There's a standard ISO 9080, and this provides a formal framework for doing this and for testing whether or not there's a knee in the curve. So you've got a load of you do your tests, you've got a load of experimental data. You want to work out whether this is just experimental scatter or whether you've really got a knee in the curve. And there are 3 ways of doing it. One is you just look at the curve with the experimental points by eye, and you try and figure out, have we got a knee there? There's also a mathematical procedure for doing that, which is described in ISO 9080. I won't describe it now. There's a mathematical procedure for testing whether there's a change in slope. And the other thing to note is that, of course, when you go from this failure line to this failure line, the appearance of the failure changes. It changes from a parrot's beak to slope crack growth. So you can see where this point is. So that's what was done. They had to change the qualification procedure, and only polyethylenes that behaved satisfactorily in this procedure could be accepted. Now the other problem I'm going to talk about in a second is what did they do to the polyethylene to make it work properly. But at the moment, let me just talk about this extrapolation procedure. Have you done Arrhenius yet, by the way? Yes, no? Everybody shrugging their shoulders. Nobody heard of Arrhenius? Poor Swedish guy, founded much of our modern chemistry, and none of you have heard of him. When something happens as a function of temperature, you've noticed that things, well, I've just said, you notice that things happen more quickly as you raise the temperature. Well, the person who put that into numbers was a Swedish man called Arrhenius. He also discovered a load of elements. He discovered a whole load of rare earth. He was the first guy to discover many of the rare earth elements. Sorry, nothing to do with this lecture, I'm digressing. Arrhenius noted that if you change the temperature, you change the speed at which something happens by that fact. Have you not come across that? You will do. You'll come across it for metals. Because anything which is temperature dependent, any reaction, any chemical reaction which is temperature dependent, at obeys this law. It obeys Arrhenius law. And incidentally, could you just make a note that there's a mistake there? That should be a minus sign. And what, I'm not going to derive it, but if you have any process which is temperature dependent, then if you do it at one temperature, and then you do it at a second, say, higher temperature, then the rate at which the thing happens changes by this factor. And it's called an activated rate process. What happens is you have some starting state there, and you have some final state there. The starting state might be that the polymer is unyielded, and that the final state is that it might have some creep might have taken place. And in between here, there's an energy barrier, which must be overcome. This applies to anything. It applies to setting of concrete, applies to setting of adhesives. It applies to anything you'll do loads of electrochemical things with corrosion of pipes, electrochemical corrosion potential. The potential follows Arrhenius law. So if you haven't come across it, you will, I guarantee that you will come across it in other areas. And this is the activation energy, which is delta H. And what Arrhenius said, everything is in motion. You know all atoms are in motion, they're undergoing thermal motion. And the more you heat up the material, the greater the motion. So if there's an energy barrier to overcome, all these motions taking place here, quite often the energy state here will jump up and down, just as a result of atoms colliding with each other. And once in a while, this energy will be higher enough for the thing to fall over the wall. And it's called an activated rate process. That's what Arrhenius did. And if you look, have I listed it up there? No, I haven't. Delta H is the activation energy. That's in joules per mole. K is just Boltzmann's constant, the gas constant. So you come across that, and that's the temperature in degree K. So just look, see what happens. You increase the temperature in degrees K, this quantity here gets smaller, but it's negative. So the exponential of it gets larger. And that describes how anything changes with temperature. So all of these curves have two terms. There's an Arrhenius term, the x of minus h over RT or KT. Some textbooks say RT, some textbooks say KT. And then this is the creep relationship. Remember we said on these curves, the log of the time to failure is a linear relationship with the log of the pressure or log of the hoop stress. So that's a straight line. So this is the equation of a straight line. If it's linear in log-log space, that means it's a power law behavior. So the time to failure is equal to a constant times the hoop stress to some power. So that governs the stress dependence. So that governs this part of the curve. And the Arrhenius term governs whether the curve moves up or down. And if you look in ISO 9080, it's a 4-parameter model. C1, C2, C3, C4. Expect you to remember that. I don't think I'll give you any calculations with it, but I just expect you to remember it. If you take logs of this, you'll see that this is what happens. So you take a log of time to failure, it's going to be equal to log of a constant, that's C1, minus a constant times log of the stress, so that's C3. And then this will give you 1 over t, so log of an exponential is just what was there originally, so that relates to the exponential term. And then there's a fourth factor which I've not talked about yet. Most of the measurements that you do with polythene, as you increase the temperature, the slope of the regression curve stays the same. Some polymers, as you increase the temperature, the slope gets steeper. This is the one that's usually used with polythene. If you work with nylon 11 or PVDF, it sometimes does this. Okay, so this is the term which is used to describe the change in the slope of the curve, the changing temperature. So if you've got the left-hand side situation where the slope is all the same, that's called a 3-parameter model. So C4 is 0. If C4 is not 0, then it gives this description of the behavior. So are we okay with that? So you understand the theory or the thinking behind that equation at the top. It's power law behavior, and it's determined by Arrhenius. I'm surprised actually at this point in the term that you won't have done it with the metals. Have you started doing corrosion and things here? And you've not got anything with it now? The corrosion potential has that's that formula. Right, here's real pipes. The real polyethylenes. This is the polythene that they use. No way would you use this polythene in a pipe now. This is the polythene that they used in the 1950s and 1960s. So here you see 20 degrees C, 40 degrees C, 60 degrees C, and 80 degrees C. Now at 20 degrees C you don't see this change in slope. So you never observe this knee. But it's an example of an older polyethylene pipe grade material which shows this transition. But as you go up in temperature, so you get up to 40 degrees C, you actually observe some of these failures experimentally during your test period. And when you got it up to 80 degrees C, you actually start seeing these new failures, the brittle failures, after about 100 hours. And just look at those curves, because there are a number of features on these curves. At each temperature, you can see they've plotted the mean line. That's the line that goes through the experimental points. And they plotted the mean line for both different processes. So they put a line through the ductile process, and they put a line through the brittle process. Now you'll notice something about those lines, that the brittle process is much more scattered, as you might expect for slow crack growth. There's much greater scatter on those experimental points than there is on the ductile process. So again, you observe all your failures up to here are parrot's beak, and all the ones beyond here are slow crack growth. In each of these cases, they put not only the mean line, but they put the lower confidence limit as well. And you can see this is what this strange inflection is here. This is the lower confidence limit for the ductile process, and here is the lower confidence limit for the brittle process. And you can see there's a much bigger gap. There's a much bigger gap here and here. And you'll ask yourself, well, how can you plot this line when you haven't got any experimental points? And the answer is, you can plot it because you have the experimental points at these other two temperatures. And you fit it to Arrhenius relationship. Arrhenius will tell you what it would do up here. So that shows it's given you the ability to observe this effect. So if you're wanting to have a design temperature of 20 degrees C, you actually got to do measurements up to 80 degrees C. And if you want to go higher than that, you'll have to go even higher in temperature. That's a poor polyethylene that you wouldn't use. Now there's some other things that you need to remember. There's a thing called the minimum recommended strength, the MRS. And that's the hoop stress for a 50-year life at 20 degrees C based on the LCL. And we have most of the pipe polyethylenes that you'll come across have names like PE80 and PE100. And PE80 means that the MRS is 8 MPa. And PE100 means that the MRS is 10 MPa. don't ask me why it isn't PE8 and PE10. I don't know. They like to exaggerate in the industry. And also the other thing another thing that you need to remember is that the pipe standards stipulate that there should be no transition from ductile to brittle behaviour within 10,000 hours at 80 degrees C, which is what you have here. So there's your 10,000 hours. Sorry, 10 to the 4th. There's your 10,000 hours. So that must not happen at 80 degrees C. So what you're going to say is that there is no transition at 10,000 hours at 80 degrees C. There's unlikely to be such a transition within the lifetime of the pipe. I'm not saying it's never going to happen, but it's not going to happen within the lifetime of the pipe. And the way they solve the problem is they have new types of polyethylene which are called bimodal, and I'll describe what I mean by that in a minute. And they show much greatly improved performance over the old linear polymers, no knee point. So there's a good polyethylene. These are typical of the materials which are used today. You'll see two things. First of all, there's the 20 degrees C line. You see there's very little scatter on that line. Everything behaves in a very ductile fashion. So there's your mean line, and there's your LCL. You extrapolate that to the design life, and that will give you. You can see that that's going to give you about 8. So that's what you would call a PE80. And this is it's a bit misleading this actually, but this is at 60 degrees C, but we should have another curve at 80 degrees C. There'll be another curve at 80 degrees C running up to 10,000 hours, and that must show no sign of a transition. Like I say, if there is no transition there, it doesn't mean that the transition is never going to happen. It just means that by the time, if you consider the temperature change, the time change with relation to temperature of the knee point, that will just simply tell you that there is no transition going to happen within the design life of the pipe. So that's the procedure. So remember these things: the MRS, which is the hoop stress for a 50-year life at 20C. So that's just the lower confidence limit here, extrapolated to 50 years. And you can see that that's a PE80 from that. You usually have, usually when you buy these pipes, they're referred to as either PE80 or PE100, but there's now a new range called PE100 Plus, which are even better. And now there's this thing about there must be no transition from ductile to brittle failure within 10,000 hours at 80 degrees C. And I expect you to remember that, like a parrot when it comes to exam. Now, model by mode, the modern types of polyethylene grades. I'm still not going to get onto I need to talk about the polyethylene grades, which I will do next time. But if you look at these curves, there are actually three possible. If you look at hoop stress versus time to failure, there's ductile failure, which we've talked about. There's brittle failure, which we've talked about. And in principle, you can get chemical behavior, this thing which I call where you see all the little cracks in the wall of the pipe. Now, it's actually, all the textbooks show the three curves like that. It's very, very rare to get all three curves existing for one particular material under a particular condition. But in some conditions, you can see that chemical failure is important. And the thing to note about chemical failure is it's not stress dependent. You see this line is vertical. So what happens is you get up to the design life and it falls apart. There's nothing to do with the stress, it's to do with the chemical action on the pipe. Right, didn't get as far as I wanted to, but Alistair was complaining that I let you all out late, so I can't let you out late now. So if I can have my samples back, I'll see you next week. I'll try to finish off next week. That's Father.
Hayırlı. Hayırlı şafaklar. Ballarını. İmran.
Cheers.